Let's see. Thank you, James. Since you're recording, would you like to introduce yourself?
Sure, I'm James Sestandra, and I also work at the Johns Hopkins University Applied Physics Laboratory, and on this project, I'm the Assistant Project Manager.
And how about Kirby?
Yeah, I'm Kirby Runyon. I'm a planetary geologist here at Johns Hopkins APL, and I'm the lead for planetary science remote sensing.
And Parisa?
Hi, I'm Parisa Mustafavi. I'm a postdoc at APL, and I work on the heliophysics and the very local interstellar media.
Great. And Reza?
Hey guys, I'm Reza Ashtari. I work on the satellite communications as an engineer for Interstellar probe, and I can't wait to hear all of your questions and ideas.
I think the last early career interstellar probe person would be Drew.
Hi guys, I'm Drew Turner. I'm research staff at Applied Physics Lab. I'm a space plasma physicist, and I've been helping on Interstellar probe with the particle instrumentation, covering plasmas all the way up through cosmic rays.
Awesome. Thank you all so much for being here with us. We're really excited to have you. And I'm going to turn things over to Reeve, who can introduce himself and who's going to be leading the beginning part of the session.
Hi, I'm Reeve Highness. I'm a design thinking strategist and mechanical engineer and systems engineer. I've worked on a couple spacecraft here at the lab. I has started working on the Van Allen probe as an intern. And then now I got a full-time position here working, help with the Space Department. So with that, I think we're going to transition over to Miro officially now. So I keep posting it in the chat. If you can't get in, please chat at us or chat at Andrea, and we'll be able to help you out and get you involved in here. Once again, hit the arrow key on the left or hit the V key so you can move around with the middle mouse button. And we actually want to know a bit about you guys. So go ahead and grab one of the sticky notes and move it on the board. We got a map of America. I can see a bunch of chat. Yeah. I see people grabbing these things. If you can't grab them, go ahead and hit the V key, and that'll allow you to use these things. We're using Miro. It's basically a collaborative sticky note software. And then if you double click really fast, you can start typing on these little sticky notes here. So we got little ones. I think there's gonna be a couple piles, maybe a couple piles around APLs. We got a bunch of people there. Oh, there's some people in Florida. Yeah, you can hit the N key to make new sticky notes as well. And then there is also the map of the world down below. Oh yeah, Sanjay, I see you're over in Europe there. Please add your institution, that would help us out. Oh, there's a huge cluster in Maryland for the old APL. So that's very nice. And yeah, if you're having trouble grabbing the sticky notes, you can hit the N key to make new ones, or remember to hit the V key to get the arrow key up. I see a couple more names joined us. So if you guys are confused where we are, we're using the Miro board. So please click on that link. And if you're ever lost or confused, message myself or Andrea on the Zoom chat, or just the public one. All right. So we got a couple people in Michigan, over in Arizona. I'm gonna start a timer for 20 minutes for this whole section. So we'll see that counting down as we keep rolling. So we keep the momentum high. Oh yeah, people are adding Florida, some in New York. Who's furthest? Yeah, Sanjay in the world. Yeah. Are University of Pisa? So that's Italy. That's exciting. Are you there right now, Sanjay? What time is it?
Yeah, it's afternoon 3.
Oh, it's 3 o'clock. Oh, so you already did lunch. Man, it's like
Yes.
time travel in the future. Do you actually see the Leaning Tower of Pisa like every day?
Yes, every day on my way to the department. Yes.
What? That's cool.
Yes.
I don't get to do that unless I got Google it, I suppose. I see like the forests of Maryland, which are pretty. Like trees are nice, but it's not quite the Leaning Tower of Pisa. How long have you been there, Sanjay?
Almost 1.5 years.
Oh, nice. Right on. It's for undergrad, grad school?
Grad school.
Oh, nice. And then I think that's a perfect transition. Oh, we got Greece. Sorry, Sanjay. Someone's coming from further away. From the when I say further away, it's in relation to me. So that's the measure. So you guys are great trailblazers. I'm glad you're from off and away. University of Athens. So do you see the Acropolis? Whoever that is, I don't see your name on there.
Yeah, hi, it's Kostas.
Hey, Kostas.
I do actually.
Oh, really? Nice. Well, I'm excited. You guys see all these architectural landmarks in your everyday. So what I'm going to do now is ask people to move down in the meeting, and you're going to see a question here. So we just want to collect a couple stats about you guys before we truly get into the brainstorming. So I'm actually going to hit the button, bring everyone to me, assemble. So you guys just zoop down here. And we want you to add in what engineering and science discipline are you most interested in. Add your name and kind of pick out from the list here. You can say things off of this list. It's just a little bit of a primer for where we want you to do, or just a little inspiration, as you will. So please pick, if you have a career path that's off here, like satellite solar panel cleaner, let's see here. What are the other excellent career opportunities for us in the future? Yeah, moon dust sweeper. People saying that. Yep. And if you're still having trouble with Miro, please message us in the chat. Once again, if you hit the V key to get the arrow to show up versus the hand tool, that's a huge, huge help. Then you can navigate around with middle click instead of just regular click. And the N key adds new boards. Astronomy and optics, I see that a lot, liking that. Please add your name in if you can to the different things here. Alice is interested in physics. I like that. She's already doing that. She already got her PhD in physics. I'm glad she's still interested in it. Because I got a couple friends getting that burnout. So don't suffer from burnout. It's okay. There is the end of the tunnel. Nice. Glad to have everyone. Nice to see everyone from doing some space particle physics. Man, everyone loves some particle physics here. I guess that's why you're interested in Interstellar Probe, because that's a lot of the science that's being done. Isn't that correct, Alice?
Yep.
All right.
Yeah, certainly talk about that.
Yes. Now let's move down. We're curious, add your name and what stage of your career you're in. If you're an undergrad, if you're in grad school, if you're employed. I'll put 8 years at JHUAPL, which that's 2 undergrads in length, is the amount of time I've personally been at this institution. Has anyone been here longer than I have? There's some serious APL lifers around. I know there are. Let's see here. Ralph, I'll pick on you. How long you been at APL?
Well, first of all, I had to figure out where the unmute button was, and I've been here way too long. It's somewhere over 25 years, and I've quit counting.
Nice.
That's, and I'm so old that I can't use any of this new software stuff. As a matter of fact, I was trying to get into Miro, and all I keep getting is a page saying that my link is expired.
Oh no. Well, I don't know if I've seen that one. If you're just clicking on the link from the chats.
Yeah, that's what I was using. If there's any issue with any software, I can always find it.
Well, I'm glad you did. You're a good canary in the coal mine. Well done, everyone. Other than clicking that link, if that link doesn't work, I'm not exactly certain what to do there. Maybe you could try copying and paste it into the Chrome browser, Chrome or Firefox.
It just keeps coming back saying your session has expired.
Bizarre. All right.
You guys go ahead. I'll try Chrome.
Yeah. Thank you, Ralph. Hey, let's go down to some juicy questions. So keep moving down, please, and I'm going to bring everyone to me. Now, let's look at this question. What should humans be doing in space by 2080? Let's dream big. Be bold. I'm actually going to give 3 minutes of heads down time. And then I'll start soliciting answers from the whole community here. Oh, we see a lot of ideas pouring in already. There's also little +1s to the left and right. If you see a particularly useful or exciting thing that you want to highlight that someone else did, I'll copy and paste and make the most recent on top objects. But yeah, double click right in about like what humans could be doing in space by 2080. That's far from now. I'm pretty excited for that. Oh yeah, I see Explorer 1000 AU. There's some Interstellar Probe excited people on here. I don't want to say dreamers because it's gonna happen. I like to see that. Oh yeah, we're really pushing here. Start a Type 5 civilization. Yeah, get out there. I love it. Spacecraft headed to Alpha Centauri. I would love to see that. I'm at a little +1 on that because I can't wait for exploring Alpha Centauri and Proxima Centauri. If anyone is joining us late to the
Just want to
Zoom
know,
link.
Proxima Centauri's got the potentially habitable exoplanet around it.
Excellent. Thank you, Drew. Let's go ahead and add that in. Add a sticky note for that. If you're curious about exploring that.
I'd like to defer to Drew then, since I was the one who added Alpha Centauri.
Yes. Remember to yes and build on people's ideas. Yeah. Who put this big orange sticky? The space tourism? Who wants to, do you want to mention a couple words about that? Was that Sanjay? Oh, you're on mute, Sanjay.
Yes. Yeah. I just would like to make space accessible to everybody. I mean, all the people who want to go to space for vacation or something. I don't know. It'll help bring more revenue. So.
Put a +1 on that if you want to go do some space tourism and travel on there. If it keeps, if it goes beneath the sticky, you can copy and paste a new +1. You know, the old recency bias thing. Yeah, we got some +1s on there now. A lot of people want to go to space. I like that. Hey, what is address CME concerns? I don't know what that is. Can someone share?
Yeah, I was just thinking about how it could cause huge power outages and maybe find more instances where big CMEs could affect our electrical grids.
Right on. I think that's coronal mass ejection.
Yeah,
that's it. I wanted to ask about the antimatter at Jupiter. I like this.
Yeah.
I'm a radiation belt physicist, so this you just got me excited.
Yeah, speak up now.
I don't know that much about it, but I read a paper once about how you get a little bit of that's probably where the most antimatter is collected in the solar system, because the sun produces some amount that gets trapped in the
cosmic rays too, actually.
Okay.
So yeah, we actually have antimatter belts at Earth as well.
That's what I heard. I just thought that I heard that Jupiter is where the largest concentration.
Oh yeah, you'll have a much higher concentration at Jupiter, no doubt, because the magnetosphere is so much bigger, the magnetic field is so much stronger. So the radiation belts there are the most intense that we know of in the solar system.
But yeah, for interstellar probes, that would be probably your best fuel, right?
Yeah.
Like way down the line.
I mean, for interstellar probe, we've got the fuel sorted out, but
right.
You know, if we're pushing towards
future.
I know this is going to make Ralph smile here. If we're pushing towards Star Trek, then
exactly.
Yeah, let's do it. I think we should.
No, but I mean, studying antimatter radiation in space is very interesting and exciting physics. So
yeah, yes, and I'm also curious what agaroscopes are. Did I say that wrong? Who put that up? Anyone want to volunteer for that one?
Oh yeah, I wrote aragoscopes.
Aragoscopes, thank you. I definitely butchered that, but hey, what are those?
So it's the opposite of a star shade. So a lot of people have heard about star shades where you can block out the unwanted interference from like an extrasolar sun or an extrasolar star. And so an aragoscope, it's basically a giant passive magnifying scope instead. So it uses a bunch of lenses inside one another in ring or an annular format, and then it provides quite a magnification. So we might be able to use that instead of some like gravity lens type experiments.
Yeah, I think that'd be absolutely cool. Put a +1 in the upper left for those
That's-
if you like those.
Is that similar to like the idea of using the sun for gravitational lensing? Like send a telescope out to the Kuiper belt or whatever?
Yeah, similar to, there's actually another company right now, I can't think of the name of them off the top of my head, but they're promoting a solar gravity lens experiment where they go out to like 500 AU or something like that, and then they're far enough away that they can use the lensing from our sun to look at other exoplanets. This would be a man-made version of, you basically manipulate the interference patterns in your favor to produce your own magnification instead.
Oh yeah, one last one. Actually filming space movies in space. I like that. So we're gonna fake the moon landing on the moon. That's super meta. Very good, everyone. All right. I'm really excited to see the future of space and all the things we're working on. We're gonna move down another one. I'm gonna bring everyone to me just to make sure we're all in the same zone here. And then what's an interesting science topic that an interstellar probe be uniquely poised to examine? So go ahead and add your curiosities. Radial transit plasma parameters all the way to 1000 IU. The heliopause, plasma gas clouds, what the interstellar medium is really measure the science behind it rather than just relying on Voyager's 1970 sensors, which is amazing at the beginning, but we can go further. Whoa, photography of the photographically mapping one of the 130 trans-Neptunian dwarf planets. Love that. Tongue twister for me anyway. Plasma densities, gas clouds. Yeah, like we really want to know the science behind this. What are all these measurements? Unfiltered cosmic rays, including antimatter. Man, we're back on the antimatter wagon. I love that. And I'm personally excited for antimatter for the engineering applications as well. Yeah, let's see what we can do with this stuff. Let's get to Proxima Centauri or Alpha Centauri, either one. Did anyone play Alpha Centauri, the video game? Quick show of hands. Yes? No? Just me? Drew did. I know he did. Yeah, nice. I like that. Cosmic rays. We got a lot going on here. Turner, do you want to mention what you're hoping to get? How we can measure these the antimatter out there in the interstellar medium?
Yeah, well, I mean, so the key thing of getting to the interstellar medium for galactic cosmic rays is that the heliosphere actually deflects away a significant portion of lower energy cosmic rays. So what we see at Earth and pretty much anywhere throughout the inner heliosphere is really just the higher energies, the highest energies of cosmic rays that are able to make it through the heliospheric magnetic fields. So getting out into interstellar space and seeing the cosmic ray spectrum there is one of the holy grails of astrophysics and cosmic ray physics in particular, because then all of a sudden we'll get this discovery of what the spectrum of cosmic rays looks like at these lower energies, which tells us all sorts of critical details on what's accelerating cosmic rays throughout the universe.
Yeah.
And then the antimatter aspect. So cosmic rays are particles. You've got protons, heavy ions, electrons, and antimatter particles. So positrons, antiprotons, etc. And again, getting insight on the antimatter aspect also tells you a lot about astrophysical processes that are happening elsewhere in the universe. And same argument holds for antimatter as it does for matter. The heliosphere is deflecting away the lower energy antimatter particles the same way as it is the regular matter particles. So it would be very interesting to, I mean, it's going to be a major discovery as when we get out there and make those measurements.
Yeah, that's super exciting. Thank you for sharing, Drew. And talking about how we can measure these things and what science we're after. I'm curious right before we move on. What's everyone's favorite trans-Neptunian dwarf planet? Anyone want to pipe up who shared that one? I don't know any off the top of my head. So if anyone wants to pipe in.
Reeve, have you
Kirby,
heard of
Kirby, how do you pronounce Quayar?
Quaoar, yeah.
Quaoar, that's it.
Quaoar,
Sedna.
but that requires you to put marbles in your throat, so Quaoar. Another fun one is Gong Gong.
Love it.
Formerly
Quaoar and
2006
Gong
Quaoar.
Gong.
Isaac, did
fan
you
of
have a
Sedna.
question?
Sedna's cool. What, Alice?
Isaac, did you have a question?
Yeah, I wanted to follow up what Turner was talking about. I'm curious if antimatter poses any risks outside of in the interstellar medium, if you have to worry about any annihilation events that you don't have to worry about inside of
So
heliopause.
yeah, I mean, absolutely right. So you can lump that in with radiation effects. So when we're talking about cosmic rays, they are ionizing radiation, right? So they're going to be damaging effects to both inert materials as well as biological materials. So if you ever get astronauts out that far, and space radiation is actually a concern across the board, whether you're working in near Earth space or in the interstellar medium. Antimatter in particular, it depends on the intensity levels. Are, as far as we know, the intensities of antimatter in space are much lower than regular matter.
So you're not going to get like a antimatter, oh my God, particle kind of situation. You know, the oh my God particle is like a baseball moving at 100 miles an hour.
Yeah. No,
particle.
I mean, you can. That's the fun thing about cosmic rays, right? But the trick is that it's probably just going to be one, depending on the size of the collector. So if you're talking a human, that's like a meter squared kind of order of area, surface area. So you might get hit with one of those once in 100 years, once in 1,000 years kind of thing. But getting hit by one, yeah, that's it could do some damage to your biology.
Definitely.
But yeah, so space radiation effects, I should say, it's a concern, and it applies across the board, antimatter right through regular matter.
I was just thinking antimatter would cause more damage than just an ionizing matter particle.
It will, well, the annihilation will produce gamma rays, which will then slice DNA and other molecules apart the same way as the X-rays and gamma rays that can be produced by a regular electron, actually, just interacting with matter.
Okay.
Once you start getting into the nuclear interactions, the secondary particles are really doing a lot of the damage, and those tend to be a lot of the same things.
Interesting.
Yeah, I think that's very cool and interesting. You're talking about destroying DNA. Reminder to not include any biological components to your interstellar probes, I think is the design features. One more that got a bunch of votes here. There's the plasma densities and the instability gas clouds. I'm not sure if that's actually a science term or if it's just instability. Does anyone want to mention what they were curious about that for the science question?
I was the one who wrote. The point is, for engineering applications, especially, plasma instabilities are poorly understood. So, I wanted maybe with the interstellar probe, we can have better plasma instruments which can measure, which can be sensitive enough to measure instabilities in plasma clouds, maybe.
Yeah, that's very exciting, and I hope the interstellar probe can help answer those questions. The next thing we're gonna do, we're gonna move down here one more time. I'll keep summoning everyone down a level. What are some potential engineering challenges involved in designing a mission to last 50 years and travel out to interstellar space, so we can answer some of these science questions, right? We want to answer the plasma cloud instabilities. We want to answer all these low energy cosmic rays. The sun is just too strong and keeps stopping in the way. Oh yeah, I see there's fuel, power, communication. Yeah, these are huge challenges. And then I'll add in my favorite. Oops, I gotta double click on this thing. Yeah. Longevity and performance of things, designing instruments the last 50 years, data compression. Yeah. I'm curious, do you guys know what size hard drive the spacecraft is going to have? Anyone know off the top of their head?
Limited. It's not really limited by I mean, there's no official spacecraft, so there's no official size, but you can pack a lot of terabytes into a pretty small size at this point. So it's
Yeah.
not too big of a concern.
Excellent. So
There
we're
are,
gonna get a
let's
lot more
just say there
data.
are much bigger limiting factors than the size of your hard drive.
I love that. So just for comparison, does anyone know the size of the New Horizons hard drive? That's the satellite that went and explored Pluto and now is going through the Kuiper Belt.
I bet Gabe Rogers does.
I think it's 64 gigabits per, and we got 2 of them on there.
Nice.
So, yep.
Launched in 2005, I think, or 2006. I don't remember which one.
January
2006.
6, but who's counting?
Yeah, right. So yeah, hard drives have come a long way. I love that. Someone talked about communication. What do you think the challenges are in communication?
So I can shed some light on that.
Yeah.
So definitely because we're going out so far, the amount of flux that we're planning on receiving back at Earth from our transmitted signals from the spacecraft, it diminishes greatly, especially because we're talking about going to distances like 300, 400, 500, 1,000 AU. And so eventually our large dishes or radio telescopes that we have on Earth, like the 70-meter DSN dishes and whatnot, they just don't cut it anymore. So what we're looking at is using these next generation radio astronomy facilities that are just, some people would think would be overkill for interplanetary comms. And we're trying to adapt those to just receive a decent data rate from 1,000 AU. The other thing that people don't think about necessarily is if you want to go to laser comms or something like optical communications, you're really limited by pointing that tight of a beam. So pointing technologies are something and that we're really looking into as well in beam steering.
Yeah, that's exciting and interesting about how all the different communications and how accurate you need to point your laser when you're thousands of or hundreds of AU away from Earth. How accurate you have to be. I think we'll take one more question here, and talking about the extreme temperature fluctuation. How cold does it get? Like how chilly are we talking? What's the what are we facing here as we go through this mission life cycle? Is it like negative 10 degrees Celsius, negative 20?
Probably more like a minus 100.
Minus 100. So as you're sitting at the launch pad on Cape Canaveral, it's a hot summer day. So it's what, 25, 40 degrees Celsius. And then everything's going to shrink as you launch it off into space and into orbit. So it'll get much cooler. So what we're going to do now is we're going to switch gears a little bit down to the presentation. I'm going to summon everyone to me one last time, and then as Alice presents the next material here, we are going to add in questions that people can answer as she shares information about interstellar probe technologies, science goals, and more. Over to you, Alice.
All right. Thank you so much, Reeve. That was really great. I hope you guys, I was really so happy to see all the different answers from everyone. So this presentation, it might be completely review for some of you and might be completely new for others, but we thought it would be a good idea to give you some kind of bearing before we start the workshop so that some of these buzzwords and some of the concepts that we're going to be talking about won't be so new, if they are new. So in this presentation, I'm going to go over the basics of a NASA mission. I'm going to go over the basics of the study that we've been working on here at APL, and then a little bit of background information about the science and engineering challenges that we've been studying. So we'll start with a NASA mission. So there, first of all, the kind of missions we're considering are missions that would be flown by the Science Mission Directorate. So there's four of those. There's heliophysics, planetary science, astrophysics, and earth science. And there are a number of different mission classes within those that range from really cheap missions like a university class explorer around 15 million or less, up to the large strategic science missions, or some of you may have heard them called flagships, which are some of you may have heard them called flagships, which are often at the billion-ish and more level. So one of the unique things about those flagship missions is that they're directed missions. So instead of being led by a principal investigator, so for example, the latest mission that APL1 is Dragonfly, which is a New Frontiers mission run by the PI Zibby Turtle. These large strategic science missions are run by the science mission directorates themselves and don't have a PI. So what we'll be kind of focusing on with Interstellar Probe would be a flagship level mission that would be most likely in the Heliophysics SMD. So a mission goes through a very long process in order to be born. So a mission like Interstellar Probe, the current area we're in right now would be kind of considered community socialization. So things like this workshop, what we're doing right now, is talking about what's important. Decadal survey studies, for example, would be another way that we might be able to evaluate what's important to the community in order to decide what missions should be flown. There are also specific studies or teams that can be developed in order to determine what should be done. So we'll be talking about something like a feasibility study, for example. And then all of this either comes before or can, in some cases, can come concurrently with phase A, which is the development of a mission. And then after all of that, which is kind of the pre-formulation stage of the mission, then you start getting into the design and the testing and the launching of the mission, which is phase B through D. And phase E is operation. So that's the exciting part where you get to get all your science data back. And then phase F is when the mission closes out. So you can see three really famous and awesome missions here. You can see Voyager leftmost, and then there's New Horizons here. And then up top is Hubble. So that should hopefully give you an idea of the kind of steps that happen in a mission. And so there are many philosophies on how one might go about formulating a mission, but one of the things that's kind of stuck with me is that you need 4 key elements. So you need a reason to go, which is the science that you're going to perform. You need to be able to get there. So that's the technology you need in order to be able to get your spacecraft from Earth to wherever it's going. You all need to agree to go or it's not going to happen. So that would be the strategy. And so those 3 are all things that we're going to be talking about during this workshop. The one thing we won't talk about is the programmatics, which is how to get the money for it. That's up to NASA. But one thing I'd like to add to this list is that I think you also need a lot of perseverance to get a spacecraft launched and taking data. So to give you kind of an example of how much perseverance you need, I thought I would give you a case study, which is the birth of Messenger, which was a mission sent to Mercury. So this timeline goes from 1996 to 2000. And so you can see in 1996, there's initial discussions beginning on what Messenger could be, what a mission to Mercury could look like. And so all throughout that, there was concepts developing, and finally a proposal was submitted in response to a NASA announcement of opportunity. And so there was a little bit more submitted in 1997, a site visit where NASA came and evaluated what had been done, and then it was rejected. So all of that's to say that you might have a really great idea and it might not pan out, but you should try again, because eventually, if you refine things enough, they're a lot more likely to work out. So another proposal was submitted in 1998, and this time after a site visit in 1999 and NASA reviewed it, it was selected near mid-1999 and the program started in 2000. So you can see it's a pretty long timeline and a lot of work to go from this concept that started in the beginning of 1996 all the way to starting to work on the mission, nevertheless launching the mission itself. So hopefully that gives you a rough idea of how a NASA mission is born and what kind of levels there are, to kind of put into context what we're talking about when we're talking about a potential interstellar probe. So I'm going to give you a little overview of the study we've been doing here at APL. So to give you some background context, which might be stealing the thunder from the overview presentation, but we'll see. we've been talking about an interstellar probe in the space community for a really long time. So in 1960, there was something called the Simpson Committee, which talked about having 3 probes to study the sun and the region around it. And so you had a probe that would be perpendicular to the ecliptic. That's Ulysses, that's already been launched. You have a probe that would come close to the sun, which is Parker Solar Probe, that's already been launched. But the one that hasn't been launched is an outer solar system probe, and one that would even be able to hopefully go out of the solar system into the interstellar medium. And so that's what we're looking at when we're talking about an interstellar probe. So you can see it's been many years that we've been talking about a concept like this, and there have been different studies and contributions and papers and workshops related to an interstellar probe. And so one of the latest things is our study here at APL, which is this pre-decadal study that started in 2018 and is going to conclude in 2022, right around when the heliophysics decadal happens.
Hey, Alex.
Yes, Pontus.
Did your screen freeze?
It might have.
Is anybody else seeing Alice's slides that she's talking about right now?
Oh yeah, I'm seeing blackness. Or the
Has it been
unfilled
blackness the whole
slide.
time?
Oh
No,
no.
mine just says Interstellar Probe Study Overview.
So let's just.
Okay, all right, that's not too long. We can fix that. I'm gonna try to share again, but if not, if it doesn't work, I might need someone to steal sharing from me. Can you see it now?
No, I'll steal sharing
All right.
really quick.
Thanks.
That's just the Miro board for the thing, and go ahead and steal it back.
All right, how about now?
Oh, it's still darkness.
Well, no, take it easy.
Yep, give it a second. There's also a sharing option that's optimized for
There
video
we go.
that works. There you go.
You see it?
Yep.
Do you see me advance a slide too? So it's not like frozen
Yes.
anymore? All right, great. All right, so interstellar probe study. One might think that one of the most important questions is what should we do? But that's not actually what our study is here to answer. So that's going to be for a future science definition team. That's for the community answer. But that at APL here, what we're trying to do is answer what could we do? So that will allow us to provide input into these decadal surveys that we conduct here in the US. And it'll allow us to assemble a menu of what has been done and what could be done with a few key requirements, because you can't really do such a study without establishing some bounding requirements. So the bounding requirements we have in our study establishes that this would be a pragmatic near-term interstellar probe, so not something that's launching way far in the future, but it would need to be launch ready by 2030. That doesn't mean it's going to launch in 2030, but it needs to be launch ready by 2030. And it need to be capable of operating up to 1000 AU, which is really far from the sun. And it would need to be designed for mission lifetime of at least 50 years. And that's really different from just having a spacecraft last 50 years. Designing to last 50 years is actually much harder. And then it would also require limited power and the capability to operate at half that power by the end of the mission, because this is a mission that would definitely be power constrained. So all of these topics will be covered in future presentations, but it gives you kind of an idea of what our requirements are for this engineering study. I'm going to flash this real quick. There's no need to read into it too much. Just to say we have a project management team, and then you're going to be hearing from them soon. We have a project science team, and then we have a mission architecture team. So we have scientists who are looking at some of the problems where there's a lot of community involvement in this. And then we have engineers here at APL who've been looking at some specific engineering challenges that might be addressed. So to kind of orient you into who you'll be hearing from when, the overviews that you'll hear today and the summaries you'll hear on Friday, those are going to come from people like Ralph McNutt and Michael Paul, who are in our project management team, from our mission architecture lead, Jim Kinnison, and from Pontus Brandt on the project science side. On Friday, you'll also be hearing from 2 different NASA systems. So you'll be hearing from the Space Launch System Coordination and also from the radioisotope power system. So those will be really, really cool updates that you shouldn't miss just because it's Friday, and I know it's hard at the end of a workshop, but they're definitely not missed subjects. On Tuesday through Thursday, there'll be different science topical areas, and those are going to be led by the science working group topical leads. And those topical leads are separated by different measurement types. And then on Wednesday and Thursday, in parallel with that, sometimes in a more plenary sense, you'll be hearing from the engineering leads about different engineering challenges. So all of those are listed out there. And then there'll be another student session on Friday at the same time from 9 to 10 a.m. Eastern time that we hope you'll join us for. That'll be more focused on brainstorming what you could do to be part of such a mission. And I'd also like to draw your attention to the networking sessions, which will happen on Tuesday and Thursday from 2:15 to 3 p.m. Eastern time, which are a really great opportunity to talk to your fellow students and early career people, but also other people who one day might give you a job. So I would really encourage you to attend those. So now I'm gonna quickly go over some background information and try and leave some time for questions. So a quick overview of the science. I'm sure there are people on this call who know way more than I do since I'm not a space physicist. But just so for undergrads who might not have heard as much of this, I want to give you kind of a basic idea of some of the terms you might hear. So the heliosphere is the general term for the bubble around our sun, which represents the sun's sphere of influence. The sun has particles it emits. It's called a solar wind, and this solar wind kind of pushes up against the interstellar medium, which is what's outside of the heliosphere, and there's this boundary region, which includes boundary elements like the termination shock, the heliopause, which is the outside of the heliosphere, and then potentially other structures like a hydrogen wall or a bow shock outside that. You have your solar system inside here. I'm sure everybody's heard of we'll say 9 planets because we're from APL and we like Pluto. And then you also have the Kuiper belt out here, which is kind of in this area outside of the planets, but maybe including Pluto, which is something you'll definitely hear about as well. And then outside of the heliosphere, you have the interstellar medium. And so this is our local interstellar medium here that's closer to our heliosphere. And there's the edge of the local cloud. And then after that, you kind of go out into the pristine interstellar medium. You have things as far away as Alpha Centauri. And for distance considerations, this right here, where we have planet X ? Is 1000 AU. So we're just talking about going into the local interstellar medium, not all the way out to Alpha Centauri. So there's several important science questions that a mission such as an interstellar probe would want to answer. So one of the overarching questions is really just to understand our habitable astrosphere. So we've been able to image the astrospheres or the heliospheres of other stars. You can see all these different examples of ones that we've been able to image, but we've never been able to image our own because we live in it. And so we'd really like to understand better our own astrosphere. Why is it habitable? There are a lot of sub-questions that fall underneath that. And I'll talk about a couple, but there are many, many more that we're considering. So for example, one of the interesting questions is how does particle flow from the sun, so that solar wind that I was mentioning, how does that balance with the opposite particle flow from the interstellar medium? So that's called the force balance. You can see here, this is like a little diagram of it using a faucet and a sink. So you have the solar wind pushing out, representing the water coming from the faucet, and that's meeting up with the water in the sink, and you have this boundary region. That's really interesting to study. And then another important thing that kind of sounds obvious given the title of interstellar probe would be to understand our local interstellar medium. So there's this local cloud around us that actually might be made up of more than one cloud and might be changing. There's a lot that that we'd love to understand about this that really can only be understood by going there with a probe. And then there's some sub-questions that are less related to heliophysics and more related to opportunities that one would have that would benefit other science mission directorates. So the planetary scientists would love to use an interstellar probe as an opportunity to explore the Kuiper Belt, for example. As you can see here, a picture of Arakoth that was taken by New Horizons most recently. So pretty cool snowball, snowman looking Kuiper Belt object. And there's actually also a lot of questions that one could answer related to the astrophysics division. So for example, there's this dust cloud that emits infrared radiation that's kind of around us. And that what's called a foreground, it ends up making it difficult to see infrared light coming from behind that foreground. And so we would, if we were to have an infrared instrument on such an interstellar probe, we would be able to study both this dust and also look at the infrared light beyond that dust cloud, because we'd be traveling beyond that dust cloud, and that would really illuminate a lot of questions about our early universe, and some really key fundamental astrophysics questions. That just kind of gives you a brief overview of some of the science could happen with an interstellar probe. So I mentioned we have topical measurement groups that have been looking into what are some of the key measurements one could make with an interstellar probe. So those are divided up. Here you have particles. So we would be looking at electrons and ions ranging from really tiny energies to pretty big energies. So that would include plasma, energetic particles, and cosmic ray instruments would be the type of instruments that would be measuring particles. You have fields, so the electric and magnetic fields, in which you'd need a magnetometer and a plasma wave instrument to measure those. You'd want to look at the Lyman alpha distribution of hydrogen, so you'd need a spectrograph for that. You'd want to look at measuring the energetic neutral atoms, which would illuminate, there's a structure called the ENA ribbon or belt. There's a couple different names for it. You can see it here in this bottom picture. It's measured by the IBEX spacecraft. And so that's a really big question as to what that looks like now, you know, why is it there? And an ENA imager would also allow us to image our astrosphere once we were outside of it. So you have low, medium, and high energy ENA imagers. And then you have neutral particles, so neutral atoms and molecules. You need a mass spectrometer, a mass spec, to measure those. There's dust, as I had mentioned, so you'd want to be able to understand the composition of the dust, for which you'd need a dust analyzer. And there's all these imagers and mappers in the UV, the visible, and the IR, which would allow you to look at this extragalactic background light and our dust cloud that I had mentioned astrophysically, and also would allow you to image Kuiper Belt objects or other objects that we might fly by and might want to image. So these are all the kind of different measurements and instruments paired with those measurements that you're going to hear about over the course of, in particular, Tuesday through Thursday. And then just to go over some of the engineering challenges you're going to hear about, mission design and trajectory is a big one. So where are we going and how are we going to get there? How are we going to get our science data down? Longevity and reliability. So how are we going to design this mission? It's going to last 50 years. How can we be sure it's going to last 50 years? Communication from 1000 AU, not simple. So that's a really big challenge. You'll be hearing a little bit about something called an Oberth maneuver, which is a particular trajectory that would use the sun for a gravity assist. So that can be really difficult for a number of different reasons. And part of our trade study has been to evaluate whether that's, you know, what that option would look like and whether it's even possible. And then guidance, navigation, and control for any spacecraft is always a big challenge. So those are going to be some of the engineering challenges you're going to be hearing about. So that's all I have. I hope that it was enlightening, and I hope that it'll help kind of orient you in the workshop so that you've heard about some of these things before if you hadn't heard about them, to kind of give you an easier time of understanding what's going on in the workshop. So I think we have a couple minutes for questions before we want to end at 9:55 so that you can take 5 minutes to collect yourself before joining us for our plenary session today at 10. So Reeve, if you want to take over with whatever the questions are.
Anyone pipe in with questions right now? I think I saw Isaac unmute himself, so take it away, Isaac.
Yeah, where exactly does the Oort cloud lie? So I guess I did have the misunderstanding that this might be a first look at a possible like to another star mission, but I understand now it's not that.
Good. That was definitely one of my aims.
So where does the Oort cloud begin? Would we be able to look at the Oort cloud? Because I didn't really, maybe you mentioned that, maybe I missed it, but.
I think we're not 100% sure, but I'll let one of the other, I'm a particle physicist. I like studying tiny things, so I'll let one of the other scientists take that question.
Sure, yes. The Oort cloud starts at about 10,000 AU, we think.
Oh, okay.
Of course, there's no evidence really out there yet. One of the things is actually that you can look at material and other things, and also KBOs and comets, of course, to give you some insight of what the composition of that Oort cloud would be. And what I'm talking about is also the so-called Oort cloud comets. They shed material that, of course, sort of rain in the solar system. That material can be picked up as well and looked at.
Cool.
Any
so
other questions?
So it'd be between the Kuiper belt and the Oort cloud, essentially. That's the area.
Yes, yeah. We would make it past the Kuiper belt, but probably not all the way to the Oort cloud.
Gotcha.
Very likely not to the Oort cloud.
Any other questions before we let everyone go?
So just in reference, considering the Kuiper belt and the Oort cloud and the question on there about Planet X, if anyone's interested in orbital mechanics and in particular early stellar system formation, one of the reasons why there is so much mass kind of out there scattered at such large distances is when the planets were forming and there was a lot more mass distributed throughout the inner heliosphere. As those planets formed, you get a lot of chaotic interactions between them. Like the solar system we see now looks not chaotic at all. It looks really nice and, clockwork, right? But that's not true when you have a multi-body system in n-body system in gravitational mechanics, right? So it's really neat if you look at some of the research on early solar system formation and how the planets, in particular Jupiter, migrated throughout the system and just flung mass out of the system. So anyone that's interested in that I would recommend you look up some details on that. It's beautiful, beautiful example of chaotic systems.
That reminds me of one quick question. Are we basically we're gonna want as much gravity assist as we can get, so we're not gonna really go at any sort of inclination, I'm guessing. Because like the Oort cloud is a sphere, right? The Kuiper belt is more like a donut, but we're just gonna stick to the ecliptic basically on this.
Yes, that's correct. The higher off you go the ecliptic, the more the penalty is in speed because you're doing a Jupiter gravity system. I saw Wayne. I see your face, Wayne, and he's our trajectory specialist, so I'm sure he can give you all the details.
Yeah, I would just follow on with that. That's absolutely right. You want to stay in the ecliptic for best speed possible. Typically, with regard to Jupiter, Jupiter is slightly inclined out of plane, so you have to match Jupiter's inclination, but it's like only 1 or 2 degrees. It's very small, but that's typically correct.
And then one item, could you please add your name and institution and level of school or career path to the chat, please? That way we got the Zoom recording going and it'll just help us keep track of what's going on. So you have to do that before you go. And then I see a question here, wait, there isn't evidence for the Oort cloud. I've heard a lot about the Oort cloud, but I guess there isn't strong evidence for it. I was curious about that.
Well, I should really defer that to our astrophysicist, Casey Liss. He's not online, but the Oort cloud, let me put it a little different way. I mean, evidence, yes, but we have never really observed it as a whole. So it's still a, not a speculation, but it's still, there's a lot missing in our picture. Let me put it that way. Does it start at 10,000 AU or further out? I don't know.
To my understanding, yeah, the evidence comes from comets with a hyperbolic escape trajectory that do not appear to be gravitationally or very gravitationally bound from the sun. And so to explain where they come from, there must be a comet reservoir from beyond that, and we've not seen an in-place Oort cloud object, but we presume that they are comets that visit the inner solar system on basically escape trajectories.
That's correct. So I mean, the other piece of this is that if you think about the other stars that are out there, at some point you get outside of the gravitational sphere of the sun, and you get into the gravitational sphere of the next neighbor, and sort of that boundary is at about a light year out. And so that's at about 60,000 astronomical units. And so that's sort of where we think that these just barely bound long period comets sort of congregate. And so that's really the reasoning that leads you to say that there is some sort of a cloud of material out there. But Honest and Kirby are right. The details are lacking, to say the least.
All right, with that, I think we should give you at least 2 minutes to make it to the overview, because I'm sure Ralph could fill the remainder. But you'll get to hear him talk really soon. So thank you guys so much for coming. Please don't forget to leave your name and your institution and your year in the chat, or whether you're early career. Let us know that as well. We thank you for coming, and we're really excited to have you at our workshop.
Thank you.
Great, thank you. I wish finals weren't early this year because they're really in the way. I'll probably only be able to make it to the ending session.
Yeah, we'll talk to them.
I think there'll be a lot of recordings posted online, if I'm not mistaken. So I think you'll be able to perhaps not participate, but at least come back and check.
Very cool. All right, thank you guys.
Thanks for coming, Isaac.
Thank you.
Thanks for the good brief, Alice. I learned a lot.
Oh, good. I'm so happy. I didn't know that you had studied so many different subjects related to space. And I did my PhD at Hopkins, actually.
Oh, you did? Nice.
Mm-hmm.
Yeah. I went to undergrad. So I'm part of the Hopkins octopus or bubble for a long time, depending on how you view the institution.
It's easy to get caught up in it.
Yeah. And you meet people, you're like, are you a doctor? You're like, no, I do nothing with medicine. I can't heal
especially
you.
getting my PhD there. It was
like, oh, you are a doctor,
that
just the wrong kind.
Not the useful kind of doctor.
Different kind. Wrong kind is the wrong word. Different kind. Did everyone do their homework within their institution?
Not that kind of doctor.
Yeah.
I don't know, with coronavirus around, I would say maybe the useless is not so wrong. It'd be great if I could use my particle physics to cure the
Zap
virus.
each Rona.
I don't think it's gonna help.
Yeah, what's the coolest part?
Guys.
Thanks.
Thanks,
you work
Drew.
with any
Thanks so much for coming.
Yeah, that was good. Thanks, everybody.
I love this stuff. That was awesome.
Everyone who's left in the chat, don't forget to add your institution to the chat. Not everyone did their homework, I can tell.
That's all right.
Yeah. Alice, well, if you have to run, you can run. But what's the coolest particle accelerator you've worked with?
I've only worked with a Large Hadron Collider. So
wow, only the coolest one.
It's the coolest one because I've only worked with that one. I think Fermilab's accelerator was dead by the time I started my PhD, but I'm not positive. I can't remember. It's all a distant memory now.
Yeah, definitely. Cool. Well, I'll see you on Friday.
Take care. Thanks so much, Reeve. I really appreciate it. You did an amazing job.
Oh, thank you. All right. Bye now.
Alice, I'm just sticking out here just to see if there's any other people just putting things in the chat. Yeah, you can,
Great.
feel free to hop off. Yeah.
I guess if you're gonna stick out here.
There's only a couple people left. I just wanted to make sure that everyone had a chance.
Okay, sounds good. I'll go ahead and log on to the center. Okay. Thanks, James.
Yep, of course.